going to talk about search and rescue over uncertain terrain. And I have, it's from our lab. So I have this John Becker, Esther Jose, and Nasran Olazad. They're sitting right here. So we co-authored the chapter together. They're three of my doctoral students. Okay, so I'd like to acknowledge, of course, the Informs Military and Security Society, who actually asked me to do this. So that thank you, and thank you, Brian, for your wonderful introduction and the opportunity. And there are a couple, some funding sources which have funded, the work which I'm presenting. There's an STTR and SBIR grant in collaboration with the U.S. Air Force. There's an Air Force Research Lab Fellowship, and there's an Office ONR grant. And the presentation structure would be, this is what I'm going to try to do. General context first, then we talk about recording emerging targets, exploring uncertain terrain, and finally optimizing information gain. So of course you can stop me anytime with questions, and so I use one of Esther's slides for the questions. All right, so for the question slide, basically if you have questions, I certainly have answers. I'm not sure if there'll be 2 questions, but I do have 3 of my co-authors, and hopefully between the 4 of us we can find the answer. We'll try. So part 1, the general context of this the talk is basically, I could present it this way. So it's a human-centered decision making for search and rescue operations during some type of catastrophic event. Okay. So let's say it's the concept is you have a UAV searching for targets or for casualties. You have a rescue unit dispatching as a second part, and then you have some sort of human-centered analysis, which would be to try to integrate these two, because in the end it's usually a human that would be doing the dispatching for the rescue team. Okay, so that's kind of the idea. Most of our work which we've done so far is in the first part, which is the search part. We are starting to do a little bit of work in the rescue part, which is kind of what we're starting to do now. And we have not done any work as such on the last part, which is the human-centered approach. All right, so this type of approach has been used very frequently. So for example, in Hurricane Harvey in 2017, they used UAVs to do reconnaissance and search for people who needed assistance. So who are the people who need assistance? And then they use that data along with other data to dispatch rescue teams, and the rescue in this case was on boats. So you have people on boats to try to get people out of who are stranded in their homes. Okay, so in this part we have done some, just to present some initial work, we can optimally solve the UAV search and routing problem, and then we introduce some alternative methods for medium and large problems. So we have a set of regions, and then you have some type of mission duration. You have flying time from one region to another. You have some type of number of people who need to be searched in a particular region. You have a detection rate for the UAV, and then you have the decision variables are the amount of time you search in a particular region before you either go back or you go to another region. In a pictorial sense, okay, so the mission terrain includes, there's a home base, and there's several target regions. So that set of regions is denoted by the set N. You have CI casualties that exist in a region. That's what your intelligence has shown, and they need to be searched. You don't know exactly where they are. The UAV starts from region 0, spends a search time SI in a subset of regions, and flies back home. The mission has to be completed in a certain time, D. So the objective is to spend the adequate amount of time in each region so as to maximize the total number of casualties you find. So in terms of if you actually do the search in a region and you spend search time SI in region I, and lambda is the detection rate of the UAV, then we have a well-known formula from search theory, which will tell you the number of casualties people you would discover in that search time. So which is Ri is equal to Ci times 1 minus e to the minus lambda Si. So it's an exponential function, which pictorially looks like this. So basically, there is, when you start searching, you find people rather quickly. And as you, and then there's a decreasing marginal return into the amount of effort you're putting in search time versus what you can actually find. So it would seem like after some time, maybe it's not really worth continuing to search in a particular region, and maybe it's time to switch to another region which hasn't been searched because you can find things more easily. Okay, and so that's exactly the principle. In order to exploit that principle, we could say, well, maybe we have a situation like this, where you would have what we want to do is have a routing for the UAV. So the blue dots are the regions where casualties exist, and you don't necessarily have the time, or it may not be part of the optimal solution to actually visit all of these. So you have to decide which ones do you want to visit, what sequence do you want to visit them in, and then how much time do you want to spend in each of the regions where you have decided to go. So here the radius of the circles around the ones where we're visiting basically represent how much time you're willing to spend in that region. The larger the radius, the greater the time. So to understand this problem, how to solve something like this, the basic problem is just a two-region problem. So if you look at a two-region problem, from that we can try to understand how to actually solve this. So if you have a two-region problem, so you're basically, in this case, very simple. You have a home base and two regions, 1 and 2, and you assume that the search mission, let's say, starts with region 1. So your available options under those assumptions is either that you spend the entire mission time in region 1, which means that you got to fly there, spend your search time, and fly back home during the mission time. Or at some point, you switch to region 2. And then, of course, come back during the correct amount of time. So if you if you did not switch, then the total number of casualties that you would have is R1 plus R1 prime. So basically, you spend a search time S1 in region 1. And if you elected not to switch, you would spend an additional time S1 prime in region 1, and then you would go back because you want to get back in the adequate amount of time for your mission time. Or your alternative would be to switch. So if you switch after spending S1 units of time in region 1, then it takes you some amount of time to fly to region 2, which is F12. That's the time to fly to region 2. And then you search in region 2, you find casualties R2 there, and then you have to fly back to the depot. So those are basically the two options which you would have. And the switching to region 2 would only be a good decision if R1 prime is less than or equal to R2. So in other words, if the additional number of casualties you could find at R1 prime is less than what you would find if you switch to region 2. Very obvious, but this is mathematically how you could do it. So that gives us, so searching for region 2, basically the options are the following: R1, R1 prime, and R2. And we can go through the math. And you basically get, if the switching occurs, we can find the time to switch, and we can get S1. If switching does not occur, then we can also get the total number. Okay. Now, to summarize it, for searching two regions, your route would be either 0, 1, 0. I mean, given that you're going to region 1 first, or 0120. And if you're going to region 2 first, it's 020. So basically, those are three options. Now, if you search several regions, we can also develop formulas to do it. But remember, one of the issues is there is the routing. So it's easy for us to solve the problem of how much time to spend in each region. What's difficult is you don't know the sequence in which you should visit the regions. So the sequence which you visit the regions, of course, is combinatorial. So you have that issue to deal with. But you're given a particular sequence of to visit, the problem is relatively easy to solve. However, you can show that we're able to show that the best, given a set of regions, the path with the shortest travel time is the best routing scenario, which is also, if you think about it, is obvious. Like that would be the best routing scenario, which means you have a fewer number of routings because you have a TSP type of solution. So basically, we have this theorem that says in a given path, we can find the optimal search time for all of the regions. So that's our result. So the pros and cons of the optimal approach. So this approach would be optimal because we are allowing for continuous time for switching. Are obviously, so I just go through these. So given a route, we can find the best search time for each region in polynomial time, so that's good. So if you're given the route, it's easy. So the problem is if you have n regions, you basically have 2 to the n routing schemes, 2 to the power of n, so that's way too many, unless the number of regions is small. And it's essentially too slow for any kind of problem instance with more than 10 regions. So up to 10 regions, you can do it. Beyond that, it's so now what do we do with medium and large size problems? Okay, so to get to the next step, we got to make some type of assumption. So the basic sacrifice we'll make is that the search time is no longer going to be continuous, but the search time is going to have some discrete options. Okay, so you discretize what your search time, and then we formulate an MIP model, which would maximize the total number of casualties, and we have a set of constraints about the path starting and finishing region. We guarantee some type of path connectivity, and you create some sort of logical relationship between decision variables as typical MIP, and then the precedence of the precedence between arrival times and of course the time limit. So to do the linearization, for the search time Si, which is in the objective function, we break it down using breakpoints. And so if this would be our way to essentially linearize the function. And then so we have a linear approximation of the objective function. And we guarantee that there's only, and to do the linear approximation, you would guarantee only using one of the breakpoints, which which search time do you actually use. And so here, the pros and cons of the MILP approximation are, you have a trade-off. You can trade off the accuracy and computational time. So that's up to you as a user. If you wanted the linear approximation to be better, you have more breakpoints, which would increase the computation time. So that trade-off is provided to the users. That's a good thing. And basically, for this, we can increase the number of regions for the problem to up to 20. So we can go from 10 to 20. Okay, which for some applications might be fine, but what if we had more number of regions? So that's our next set of slides. So here what we would do is we would do a clustering of the regions, and we would basically cluster the casualties, and maybe it's a picture which I can show. That'd be easier. So you have, in this picture, there are 4 clusters. And so you have, yeah, so basically these are the regions. The regions are the little circles, and so you would cluster the regions. And now what you do is you would say, you k-means for the clustering, and you say, well, what is my sequence of clusters? What sequence should the clusters be visited? Maybe we don't visit all the clusters, but decide which clusters to visit and what sequence do you want to visit them in, and how much time do you want to spend searching in a cluster. So once you get inside a cluster, then you have a fewer number of regions that are in the cluster, and you reapply the same thing. Now you're in that cluster, I have a certain amount of time that I want to spend in the cluster to regions that belong to that cluster, and how do I allocate that time? So basically, just break it down into, reuse the same methodology, but in that way. And of course, one of the things you got to decide is how do you go from one cluster to another. So where do you enter a cluster and where do you exit a cluster? So that's one thing that we have to also consider. Okay, so in terms of, so that's kind of summarizes this first piece of work, which is also serves like an introduction to the whole, to what we've done. And so as the density and distance of the clusters increase, we can show that the heuristic actually converges to the optimal solution. But the question is, how do you find thresholds for these metrics? Okay, so that's one issue that we want to study. And in terms of computational testing, we are planning, so this is we haven't completed this piece of work. It's, I would say, 75% done. We have about 25% left to get a paper out. So the parts which we have not done is a base comparison to solution methods, some sensitivity analysis, and a case study. So that's the part we are working on right now. So that actually concludes the first part of the talk. Any questions about the first part?
Thank you for the information. And I'm wondering for the first part on the search mission with UAV. So essentially, we are using UAV to get the rescue requests in each area.
Yes.
And then you are assuming that rescue was conducted first, and then search was conducted first, and then you send out the rescue teams.
That's correct, because normally if you try to combine them, that's a very inefficient way to use rescue resources.
Okay.
Because rescue resources are very expensive. You typically want to try to avoid, like say a helicopter has to pick up casualties. If you use it also for searching, then it's really, you're not utilizing the rescue resource. Yeah.
Yeah, so I understand this is like a stylized model with like one UAV.
This is just one UAV. So you could have multiple UAVs, though actually many applications where they do it, what they first decide is they take the whole area and you'll break it down into sections which would be searched by a single UAV. Yeah. So I think from a bigger sense, it's quite typical to have a region which would be responsibility of one UAV.
Okay, understand.
Like you would typically not send multiple UAVs on the same section where you want to search.
Okay, so in this sense, will there be related research on how did you dispatch multiple UAVs by like clustering them into different areas?
Yes, there would be related research on that. Yes.
Okay, thank you.
Oh, absolutely. Yeah. Okay, so part 2 is to do with recording emerging targets. So these are basically things that emerge. So in a military context, it would be you have a region and targets. These are potential threats or potential enemy positions that are showing up, and you don't and they are going to emerge as you would search. In humanitarian context, for disaster relief, it would be these are casualties which appear and become visible to you. So basically, UAVs, of course, in the military applications are used for several types of activities like attacking, surveillance, rescue, and reconnaissance. Many different uses of UAVs. So route planning for UAV surveillance is actually a very popular topic in the research domain, in military and security applications. And most of the time, it's done in the context of where you have information about the targets. So you have some information about where potentially the targets are, and you're going to use that information to actually guide the search. But there are many situations where actually you don't really don't have any information about the targets. You have some information about where targets might show up, but you actually you don't know any actual targets that are there. It's like there's a field, you don't really know exactly like where these targets are. You have an idea of where they would show up. So that's where we are designed. So for our situation, there are basically no targets before the mission starts. So there are no actual targets where we know the positions of these targets where we would go and try to find them. So we would have basically the accurate information on targets is kind of unknown. I'll get into what we actually know about it. And so we propose basically two methods to do this. We do an orienting problem with time windows as one method, and essentially we try to optimize what the time window should be for each region. So we try to think like, okay, so design the search using time windows for each region. And the second method is a taboo search. Okay, so what is our system? So let's say you have an area of operation. So in this case, the grids. So the 16 grids that are shown here. And each of these grids basically has targets that are emerging. And we can think of these emerging targets. There are four types of grids. There's a type B, in which the targets mostly arrive at the beginning. There's a type E, where the targets mostly arrive at the end. Okay. There's a BE, where targets arrive at the beginning and they arrive at the end. And then you have type S, which is basically they kind of arrive throughout the whole mission duration. So basically for each cell, it's categorized in one of these bins, and you have these functions that's available to you. Okay. So that's the data you have. Okay, so and then basically the factors related to the UAV, you have the sensor capture radius, which is essentially how large the UAV can detect, and how fast the UAV can move, and the UAV service time, which is how long the UAV requires to route a specific region, to record a specific region. Okay, so basically here's a problem statement. No targets really exist before the execution of the mission. The targets emerge while the UAV is conducting the mission, so targets emerging. The targets, we assume, follow some type of non-homogeneous Poisson process because it's not homogeneous in time. It's non-homogeneous as was shown in those graphs. And so this really, so the targets emerge according to these arrival rates, which are non-stationary. And then basically the UAV is assumed to move from the center of one cell, then to visit another cell. So the UAV does not know anything about the targets prior to their arrival, but it can discover them as it's flying over them. And the functions of arrival rate for each cell is what you know. That's what you know. And we of course have a maximum allowable time for the mission. So basically we have, this is what's given to us, is these, for these 16 cells, we know the arrival rates as following a non-time homogeneous Poisson process for each cell. So this is empirically given to us. That's the data we have, is the those empirical pictures. So how difficult? So what we basically want to do is develop a route which would maximize the number of targets we can observe. That's the aim. So why is this a difficult problem? Because the only thing we have is this. And we don't, obviously, this is not going to tell us with certainty how many targets we can find. We can only talk about, for example, the expected number of targets. Okay, because all of these are Poisson generating functions for targets, which doesn't actually tell us precisely how many targets will be there in a particular region. This is the rate at which targets appear. So it doesn't make sense to talk about like maximizing the number of targets, because the number of targets you would get on any particular routing is in fact a random variable. So we can only talk about maximizing the expected number of targets, recognizing the fact that it's a random variable. So basically, so that's certainly one challenge. We can realize that right away. And so it's also quite difficult to formulate this as a mathematical model. Like, how do we start with that? Challenging, because basically these are just empirical functions that are given to us. So in each region, we have an empirical function, which is the target arrival rate. So that's a very practical input, but it's difficult to deal with from challenging to deal with from a mathematical. So what is the approach we can really have? We could develop some sort. So the approach we thought of is, okay, we'll develop some type of routing. Like, we'll have a method to develop how to generate a reasonable route, and we're going to do that using the easiest way is orienteering problem with time windows, and we'll select the time windows intelligently for each region. And then once we have a route, we can evaluate the route with simulation. So basically, you have a route, and now you simulate. You simulate the arrival of targets, and you simulate what that route would actually achieve. And you run the simulation enough times, and then that would give you an idea of the average number of targets that that particular routing would be able to achieve. Okay, so that's the approach. And then, if you like, you could maybe change the route and then redo the simulation and try to improve it. Okay, so that's the idea. So how to simulate? So simulation is basically just shown that is relatively easy to do. So if we have these empirical functions for the temporal Poisson process, it's relatively easy for us to simulate the arrival of targets in each region. And what do we do in terms of the time windows? So for the time windows, if it's a type B cell, the targets arrive at the beginning. Now, targets, we're assuming in this case, are not able to camouflage. So there's another study we did where the targets can camouflage, but let's assume the targets cannot camouflage. They can't hide once they arrive. Then if they arrive at the beginning, it doesn't really matter too much when we go, as long as we don't go right at the beginning. If we go in the middle of the mission or we go at the end of the mission, we're going to find, because the targets will be there. Okay, so that's the guidance for the time window. If they're arriving at the end, which is type E, mostly arriving at the end, you don't want to go at the beginning because there'll be basically nothing there, or very few targets. You want to give some time for the targets to actually accumulate and then go and grab them. So to type E, you would want the time windows to be set towards the end of the mission. In B and E, that's a tough one. So if you want to go, if you go in the middle, you're going to get the ones that came at the beginning, but you're not going to get the ones at the end. If you go at the end, then you're going to get all the stuff that came. So obviously, going at the end is beneficial for everything because nothing can camouflage. And then type S is where it's kind of it's flat. So here, also, of course, it's better to go at the end, but there's no obvious strategy that you would use. So you got to try to decide what the optimization of the time windows for the orienteering problem with time windows. Now, if it's camouflage is there, it gets more interesting because now camouflage, we have a camouflage rate. So target appears, and then once it appears, it's going to disappear in a certain amount of time. That's according to a camouflage rate. All right, so that's basically the gist of part 2. So, and then of course to do the study, we conducted a factorial design experiment, and the The factors were the sensor capture radius, the UAV speed, and the UAV service time. Those are the three factors, and we studied the impact of those factors on these decisions. So this piece of work is complete, has been published in Military OR, and the second part of it, which is to do with camouflaging, is Journal of Defense Management and Simulation. Journal of Defense Modeling and Simulation. That's the second part, which is the camouflage. Part 3. But before that, I'll take any questions from part 2, which was to do with the emerging target.
So I'm curious about these non-homogeneous spatial processes. That is very intriguing. Is there a context where somehow that's available beforehand, some tested, or like, how are they parameterized, that sort of stuff?
Right. So we're assuming that that's basically the data that is available to some sort of intelligence. Okay. So the data is this non-homogeneous Poisson problem, which is actually very realistic, because that's typically the type of thing. So our challenge was, we first thought, okay, we'll try a mathematical approach to this. But you could do a math programming type of approach if we made some assumptions of like they're basically maybe in linear steps and stuff like that. But it gets very complicated very quickly. So we decided to just completely avoid that and use a math programming approach essentially to develop the search route using orienteering problem with the selected time windows, and then evaluate through simulation. So we just came up with a totally different approach. So basically, what we're trying to do in all of this is trying to do problems which are, they take a different type of modeling approaches to what's been done in the past. So here, the next part of the talk is, part 3 is exploring uncertain terrain. So how do you explore uncertain terrain? Okay. And so in a sense, develop a routing procedure for traversing and learning on a stochastic network. So you're going to learn about the network and then and route as you go. So there's a problem that's been studied, which is in vehicle routing, which is similar. It's called the Canadian it's the Canadian traveling salesman problem, right? So I believe that's what it is. Canadian traveler problem. So the Canadian traveler problem is you have a road network in which essentially you can only find out the status of a link if you get to one of the end nodes of that link. So some of the roads work, some of them don't work. You actually have no idea. But once you come to a node, you have a concept of, can I actually use the road or can I not use the road? It's called the Canadian traveler problem because it's from like snowstorms that occur in many parts of Canada, including Buffalo, where we live. Of course, we're not in Canada, but also we get snowstorms where you don't necessarily know whether the road is passable till you actually get there. And so, okay, can I actually go here, or should I not go take this section? Okay. So the Canadian traveler problem was to try to find a route where you can visit as many nodes as possible and basically reach where you want to go within a designated amount of time. Okay, that's the concept. So we propose a Canadian price collection problem. So they're different. The prizes are like associated with you're trying to search and find people, maybe rescue them. And so you want to develop this Canadian price collection problem, which is what we did. And so essentially the way I would show this is the following. In the graph, we can see. So you have a graph. So S is the first node. The labels are the nodes, and then the prices are the second label on the nodes. Okay. So S is where we start. T is where we end. Both of those have prices of 0, and then your prices. All the other nodes have an actual price. If an edge has a number next to it, that is simply the amount of time we would need to traverse that edge. If it has a number and an M, that means we don't know whether that edge exists. Like, for example, this particular edge here, we don't know if it exists till we actually get to B or we get to G. So if my vehicle is at B, I'll that information will be revealed to me whether that edge works. If the edge works, it has 4 units of time. If it doesn't work, it just simply doesn't exist. So obviously, there's a ground truth. There are many possible ground truths associated with this. So one possible ground truth, only one of them obviously would be the actual situation, is shown on the graph in figure 7 on the right-hand side. So in this, for example, you can see that this particular edge joining nodes B and G actually in reality doesn't exist. But this edge joining G and H in reality exists. So some of these M's are actual realizations and some of the M's don't exist. Obviously, we don't know the ground truth. If we knew the ground truth, then the problem is very simple because it's a standard price collection problem on that ground truth graph. So the difficulty is we actually don't know what the ground truth is, but we do know which ones are known with certainty and which ones are not known. So we don't really have probabilities associated with these. So that's the important thing, is where we stayed away from probabilities, because from a modeling perspective and from an application perspective, using probabilities actually is problematic, because you have to get estimates of those probabilities. You have to get estimates of the correlation between different edges working. So we're not dealing with estimates of what the probabilities of an edge working or with the correlation between different edges working. We're just simply saying the some that work for sure, some which we know, we're uncertain about, but it's only going to be known to us once we actually get there. We're going to discover whether it works or not. And of course, there's only one ground truth. So that's the problem setting that we have. So we try to keep the problem setting to be very practical from an application perspective. Okay, so that's a problem setting. So obviously, this is not an easy problem, because first of all, I can't even guarantee that I can get from S to T in the mission time. Because what if I start going to areas where things, maybe there are large prizes associated with nodes, but to get to those nodes, I have to go through some edges which I actually don't know whether they exist or not. And I try that, and I find out they don't exist, and then I kind of run out of time and I can't get to T. Okay. So if you're not careful and you start going on a route where you're exploring, you may not be able to get to your destination in time. Okay. So essentially, there are two strategies to this. One is first focus on simply getting to your destination. So that's one strategy. Just try to get to your destination as quickly as possible. So intuitively, the strategies would be, let me get to my destination as quickly as possible. That itself might not be, maybe there's no path with all. So if I remove all the M's, like in this example here, if I removed all the M's, then actually I don't have a path that goes from S to T. So even if I'm just interested in just getting to my destination as quickly as possible, I'm not going to necessarily be able to do that with the guarantee of the time limit. Okay. But what I'm going to do is first focus on doing that problem, is getting to my destination as quickly as possible. And I might have to go through, go to uncertain regions, but I'm going to, one way to do this is just first find the shortest path from S to T, assuming that everything works, and go on the shortest path and discover edges, and now you keep updating your network and you keep resolving the shortest path problem. And so that's one way, because once you go to a node and you discover that a certain set of edges don't work, you remove those edges from the graph and you resolve your problem. and you aim to get to the destination as quickly as possible. Once you get to the destination, you have a certain amount of time that's left over. Okay, let's say the total mission time was 50 units. You get to the destination in 25. You have 25 units left over. And in the meantime, in getting to your destination, you've discovered what things on the graph actually work. You can try to get to the destination, take the remaining time, and in the remaining time, you have, in the process of getting there, you've kind of discovered what things work. Not necessarily the entire graph, but you've discovered a lot of things about what works and what doesn't work, what links work. And you have an idea of the remaining prizes that you know, the ones you haven't been able to collect. And now in the remaining time, you just go and try to collect those prizes and come back in the mission time. So certainly that's one strategy one could use to solve this. Get to your destination as quickly as possible and then use the remaining time. The other way to do this is say, well, maybe that's not going to really give me maximize my the amount of prizes for me. So maybe I should use some sort of mixed strategy, which would be what we came up with was we have some intermediate destinations. So if we have an S and a T, we create intermediate destinations, which are areas where large amounts of prizes exist. And we say we divide our mission time into components, and we say, well, we're going to go from the origin to our first destination, which is just artificially created, where it is, and that area has a large number of prizes. And then we go to the second one, third one, and so on till the end. So what we do is we break up the problem into components, and in each component, we use the same strategy. So I think that, in the interest of time, that actually summarizes the third part, which is basically over collecting information over uncertain terrain, routing over uncertain terrain. Okay, so again, our goal, just like it is pretty consistent, what we're trying to do is make assumptions which are actually much closer to what we would see realistically. So we completely avoided like probabilities, correlations, all that stuff. It says basically there's a ground truth, something works, which is not known to us, but we do have what is typically known is some things that work, that's known. We have 100%, and the other ones we just don't know. We discover as we progress. So this paper has been published in also published in Military Operations Research. This is the one over there. So last part is about optimizing information gain. So this is an application which is most from a satellite. So if you're using satellites to collect information, and you have information map. So in this particular case, the darker the red, there is more likelihood of something valuable being there in that cell, and the ones which are lighter shaded are less likely. But anything could, of course, contain what we're looking for, or what things we are looking for. But that's the heat map, if you like. And so you have the cells with the highest information gain, and you only have a limited number of readings that you can take, which could be limited for a number of reasons. One is simply data. So a satellite typically has the one thing that's true about a satellite, it has a finite source of energy. Okay, so a satellite is essentially getting energy through solar. That's the principal form of energy. There's really no other form of energy that the satellite has. So it has to use that energy for everything all the functions that it does. Those functions could include maybe alteration of the satellite trajectory through movements of motors, which would alter the trajectory. It could include any communication which the satellite has with a computing center on Earth. Like it's got to communicate the data it collects. Maybe it's collecting some imagery data. and then it has to transmit that data. Okay, that requires energy. So all this requires energy. Once the satellite runs out of energy, it's basically done. So basically, it's collecting solar energy, storing it in some sort of battery, and it's using that energy. But once the energy goes, so you cannot violate the energy constraint. It's a hard constraint. And for that reason, you typically cannot take too many observations. Because an observation requires energy, because you're going to actually either take images, or you're going to actually take videos or whatever it is, and then collect that and send it. Okay, so that's the concept. So you have a limited number of samples you can take, and the question is, where should you take the samples? Okay, so now we changed the computer, so I'm going to have to figure out how to do this. Okay, very good. So basically, the concept is maybe we shouldn't sample just where the highest information gain is. Perhaps we could be a little bit more intelligent about it, because we can get information about cells where we don't necessarily sample through data fusion. So if I sample, for example, in two cells, 1 and 2, and those cells are not very far apart, then I can get information about a cell that's in between, with this question mark is, through some type of interpolation method. Okay, so I could say, well, if I've done 1 and 2 because those are the actual observations, but maybe I can get something about this question mark cell, and that would be a function of the distance from these particular observations. So the greater the distance from the observation, the less that would contribute. And if my third observation is very far away, then that's not going to help me with this question mark cell. So this concept is well known in geography. It's called kriging, which can be used basically as a fusion technique. So, for example, you could have positive correlation, which means if a particular cell had information, then cells around it are very likely to have information. That's like completely positive. Or if a cell doesn't have information, then the things around it are not likely to have anything at all. You could have negative correlation, autocorrelation, or you could have no spatial correlation at all. So obviously this technique is not useful where there's no spatial autocorrelation. So if you expect that your application does not have any spatial autocorrelation, this would not be a good method to use. But if you expect some type of autocorrelation to exist, then this would be useful. Okay, so how does kriging work? So what we're trying to basically do is we're trying to find out where the sample should be taken, so that the number of cells which we have some degree of certainty about is maximized. So basically what we want to do is we want to be able to have some degree of confidence associated with observations in a cell. So it doesn't have to be that we have to actually observe the cell directly, because that is only done through the sampling. But if a cell has the uncertainty associated with that cell is reduced beyond a certain level, then we can say that that cell is covered. So that is this concept, of course, with information fusion. You have a variogram, and essentially this is the uncertainty level associated with that cell. Okay. And then you have your estimation, and you have a variance associated with that estimation for each of the cells. So basically, if you have you sample, you have certain cells that you have sampled, and now based on that, you get for every cell, including the ones that you haven't sampled, you get an estimation, and you get a variance associated with that estimation. And so the question is, where do you collect the data from? And obviously, where the number of samples you have is very large in terms of the possibilities. So that's the combinatorics of it. And Then the other aspect is associated with the in a satellite. You also have, you could take the sample at different resolutions. Okay, so if you had, so you have to decide not only what, like the sample, where you want to sample, but what resolution do you want to take the sample. So that's another consideration. And our approach is to convert this to MIP. Okay. And in the conversion to the MIP, we recognize that this basically covering a cell with a certain degree of confidence becomes equivalent to a distance constraint, which is actually much easier for us to implement. So essentially, if a sample is within a certain distance of a cell, then that particular cell can be covered with a required degree of confidence. And that is related very much to coverage problems. So then we realize that this particular problem is essentially a coverage problem. So we have this concept here where a cell is covered if there is a sample within a certain distance. And of course, that also depends on the resolution of the sample. So a certain distance. So the distance is a function also of the resolution. Okay, so that is the essence of it. We have, you could have a spatial, so if you had a larger scale problem, you could use clustering methods like we had used earlier in the talk for in a different context, where you have a certain number of samples that you can take, and you have clusters of, you use your heat map and you cluster it, and you say in each cluster, how many samples, you first decide how many samples should I use in each particular cluster. So that's like the high level problem. And now you go into a cluster and you say, well, I'm taking 5 samples in this cluster. Where do I take the 5? So you kind of break it down, which is completely logical because the heat maps are typically have clusters, and you know that if you take a sample which is very far away, then that sample has no effect from, theoretically has no effect on the, in reducing the, or increasing the certainty associated with a cell that's very far away. So basically, if the clusters are sufficiently far away, then the samples in one cluster have no positive or negative effect on samples in another cluster. So logically, if the clusters are separated by a significant amount of distance, you should be able to break up the problem into how many samples in each cluster, and then within a cluster, where should the samples be taken? So that is basically the approach that we have used here. And this paper is, and there's a linkage with this with the maximal coverage location problem, is probably about a month away from being completed. So that's all that I had. Any questions about part 4 or any questions in general?
Thank you for the very insightful presentation. This is a very condensed 1 hour or so presentation. Where could I read more about techniques and heuristics being used?
In the heuristic techniques here, in the last part? Yes. So the last part was, so the MCLP, the maximum coverage location problem, taboo search is the one method which has been the most productive.
Yeah.
And so that's the one we used, yeah.
Yeah, I mean actually across the entire presentation, where could I find more, more about the techniques that's being used?
Oh, sure, absolutely. So a lot of the presentation and the papers are published. So I could give you, so we have the tutorial is in the Informs tutorial book.
I see.
And so we have a chapter and which details all of this. And that chapter includes the references of these papers, which I...
Sure.
Yes.
Yep, thank you.
So it's there, yes.
Awesome.
Yep, absolutely. Yep.
Yeah, all Informs members should have access to the tutorial that accompanies the presentation. So you should be able to download it, and all the tutorials are available for informed centers.
Yes.
We can conclude the presentation and thank Dr. Bhatta for a very great overview of methods here.
Thank you. Thank you.